So we're going to be talking about all kinds of receptors, channels, hormones, you name it. Okay? So here we go. Strap in and let's do this. All right. Also, if you see something in green, you know it's going to be on the test. So that's your first little hint. If you see any sentence or whatnot in green, and more importantly, when you see this in green, and I ask you to give me the definition, it must be verbatim. Who can tell me what verbatim means? Word for word. Thank you, Andrea. Yeah, word for word. So right off the get-go, homeostasis, the maintenance of a relatively stable internal environment. And we use the term relatively stable because things change. Your body temperature goes up, goes down, your blood pressure goes up, goes down, but hopefully it stays in a range that we can live with. So there's your first, and this will be on the test, and you will spout this off verbatim. Okay, so again, the whole focus of AMP2 is basically homeostasis. Everything that we look at, the heart, the lungs, the kidneys, the endocrine system, it's all about homeostasis, all right? And so it could be homeostasis at the cellular level, where we're just talking about cells, I don't know, something as simple as blood clotting to stop you from bleeding. Or it can involve an entire organ system, or it can involve, and this is what you're going to see a lot, it can involve several organ systems working together, as you're going to see, to, again, keep us in homeostatic balance. All right. And this is when you'll see lots. So we kind of look at the homeostasis in compartments, all right? So we have our extracellular fluid, which is simply that, everything outside the cell. So that includes the plasma and the interstitial fluid, the fluid that just surrounds the individual cells. And then we have the ICF, intracellular fluid, which is inside the cell. And so this is kind of like just a quick understanding of where we're going in this course, all right? So we can take, something as simple. Okay, good gosh, what's going on in the chat board? Oh, everybody's just getting their email addresses. All right, so let's talk about aerobic respiration. What's aerobic respiration? Somebody, why do we have aerobic respiration in our cells? What are we trying to make? Anyone? Oh, no, we don't want to make carbon monoxide or carbon dioxide. Carbon dioxide is a byproduct. But yes, very good, Christine. We want to make ATP, adenosine triphosphate. That is our energy source. So, and believe it or not, you will have to learn the equation for aerobic respiration, not this instant, but I expect you to ultimately be able to tell me that, hey, yeah, we start out with glucose, C6H12O6, plus oxygen, and we go through a series of metabolic pathways, and ultimately we get water, CO2, carbon dioxide, and ATP. So this is kind of a little thing. So for instance, I need oxygen. So our external environment has our air that has the oxygen. Our lungs are going to extract that oxygen, and you're going to learn exactly how they do that later. And that will enter, the oxygen will enter our bloodstream, deliver the O2, diffusion, until it gets into the cell where we can make ATP. So that's just a really simple version of it. And as we said, we do have a byproduct of CO2, and we don't want too much of that. So the CO2 will diffuse, and get to the lungs. We will exhale it. So again, that's just a very simple overview. We'll get in more details later. So when we talk about homeostasis, the two main systems involved is the nervous system and the endocrine system. And of course, the endocrine system will be our first unit to go through on Wednesday. All right. Boom. The nervous system, in terms of homeostasis. Boom, boom, boom. Yes, Daniel.
Yeah, sir. I was just making sure you weren't presenting because it sounds like you're looking at documents. Because I'm not seeing anything. I'm just seeing a black screen when you're talking.
Anybody else having that problem?
I see the PowerPoint.
Yeah.
All right, I'll just refresh.
Yeah, refresh. And you know, you might have to do that throughout this course, is if something's not working, just, you know, refresh, log in, or log out, log back in. All right. Yeah. That's usually a quick fix. Yeah, because yes, I'm not saying this off the top of my head. All right. So as I was saying, hopefully Daniel will fix his little issue there. The nervous system, when we talk about homeostasis, is a rapid response, a quick fix. My blood pressure dropped too quickly, and so I'm going to ramp it back up through the nervous system and the heart. It's the endocrine system that really regulates homeostasis over the long term, making sure I have just the right amount of sodium, potassium, glucose, all those things. And you're going to learn all that stuff in this course. Okay. All right. So, and hopefully you guys, I'd like to think you guys are taking notes, not just listening like it's on TV or something. Because if you take notes and make some little, maybe a little rating thing, or this, hey, he made a big deal about this, not so much about that. So some sort of way to prioritize, it'll help you. So just for fun, you know what I'm going to do with this slide right here? Anybody? Anybody? Christina. Okay, Christina's going to be funny. Oh, no. Delete it. I don't think so. Yes, and you got it. So any parameter, and you're going to get a lot of parameters in this course, and any parameter you see, you know it's going to be on your test. You know it's going to be on your test. So this was just to emphasize that. Now, you really don't know what 100 millimeters of mercury really means right now. You will. So for right now, until we get to the respiratory system, you just have to memorize that the amount of oxygen in your bloodstream on the arterial side is 100 millimeters of mercury. And the CO2 on the arterial side is 40. You just have to take that as face value till I explain what that means in a couple of weeks. Your pH, this is valuable. You can see this pop up all the time. And this is for your ECF. Your pH in your cells is a little bit different, but this is the pH, and that's going to be critical. A lot of our organ systems work to maintain your pH, including your lungs and your kidneys. Blood volume, depending on the size of the individual, can be 4 to 6 liters. So if I give you a problem involving blood volume, you're going to say 5. 5, all right? Blood pressure, 120 over 80, although my doc friends tell me that now they're going to lower that to 110 over 70. Whatever. And again, we in physiology and science, we use the metric system for everything. So your temperature is in Celsius, and so that's 37 degrees. That's the same as 98.6 Fahrenheit. So you will see all these on your first test. First test. So again, the whole point of this course is to teach you how your systems work together to maintain homeostasis, because it's constantly being disrupted. External things, hot, cold, lack of oxygen, pathogens, you name it. And then you have internal things that are constantly in dynamic change, temperature, body temperature, blood pressure, concentrations of these critical things that we're going to learn so much about. And of course, even your stress levels, physical and psychological, can affect your homeostasis. And again, once your systems cannot maintain homeostasis, bad things happen. Okay, so quickly, how it works in our body is we have lots of receptors. These receptors, for all kinds of different stimuli, need to detect a deviation from the norm. They need to send that information to some sort of integration center. It could be the brain, or it could be just the spinal cord, or it could be just another organ. We'll see lots of variations in that. And we have to be able to adjust to respond and get us back to where we need to be. So we have intrinsic, and intrinsic in physiology in this course basically means at the local level. Something's happening at the local level. So as I mentioned earlier, an example of intrinsic control would be if you cut yourself. All right, when you cut yourself, hopefully the coagulation process will start and we can stop the bleeding. So that was a local thing that happened. Extrinsic usually involves the nervous system and the endocrine system, and we're looking at the big picture here. All right. Boom. We have several different types of loops, if you will. Some of them aren't loops. The feed forward, not a big deal. That's one of those rare things where we anticipate a change, but a change didn't happen, but we responded to it. So yeah, thinking of food, the smell of food can get your gastric activity going before you even had a bite to eat. Feedback is where we are most of the time. And we have negative feedback and positive feedback. And again, this is not the negative feedback like you're getting yelled at. The negative feedback just means, hey, I detected a change and I want to get it back to where it was. And that's by far the most significant feedback system we have. Positive feedback is we detect a change and we want to continue the change. And these are very rare. Much of it has to do with reproductive activity, especially like childbirth and location. And we'll give you an example. So this is a very important slide. How many times did I say that, somebody? Christina says 4. Daniel says a lot. Okay, so Daniel, you got on, so we're good, huh? Okay. Yeah, folks. And I'm telling you right now, I'm just giving this to you. It's a freebie. This is going to be on your test. All right? I expect you to be able to give me the components of a negative feedback system. And so it goes very simply. I have a change. Something changed. Lots. You're going to see so many different negative feedbacks in this course. You have lots of examples to go to. So we have a change. I have a receptor that can detect that change. I'm going to send it afferent. Hopefully you guys remember what afferent means, to some sort of integration center. It could be, like I said, the CNS or endocrine. I'm going to have an efferent pathway to the target, and I want a response. The reason it's called negative feedback is, you see this dotted line right here? This dotted line means to stop, to inhibit. This isn't in the right color. Hold on. I don't know what it looks like on your slides, but let me just do this real quick. All right. So now you can see that dotted line means stop. And what we're saying here is I detected a change. I want to fix that change. I want to get it back to normal, but I don't want to overdo it. So if my body temperature gets too high, I want to make the changes to get it down, but I don't want to get it too low. So negative feedback means I make a change, I correct back to normal, and then I stop. I don't want to go any further. So I expect you to know this, and ultimately you're going to get plenty of opportunities to give me an example of this. So your question on your test is going to be, hey, outline the components of a negative feedback system and give me an example. And we're going to give you a couple examples even today. All right, so positive feedback is, like I said earlier, you have a change, but you want to continue with this change. You want to keep going, keep going. So you see this line here is solid, means keep going, keep going, keep going. And we'll give an example here. Now, you will have an opportunity to provide an example of any negative feedback system. Some of these might be a little bit difficult for you because we haven't really covered it. So don't let this scare you right now. You might want to return to this. So some of these examples may be a little bit more complicated because you don't really know this information. So this one will make more sense when we get to the endocrine system. But we do have our thyroid hormones, T3, T4, and they have to be at just the right levels. And so it's the hypothalamus that monitors those levels. And if there needs to be a change, if the levels are too low, then we have a cascade of reaction. And I'm not going to go through this whole thing because you're going to see this exact same slide when we actually get to the endocrine system and the thyroid gland. So basically all you want to get out of this right now is you go through this entire process, get the thyroid to release more T3, T4. Once I get to where I want to be, I shut it down. I don't want it to go any further. Again, don't let that one worry you. You'll be an expert in that in a couple days. Here's much simpler, and always go with a simple thing if you can. And so here's a very simple negative feedback loop. I have high blood pressure. I have baroreceptors. If you don't know this, baro refers to pressure in the walls of your carotid artery and aortic arch. And if the pressure is high, it's going to send a signal via the vagus nerve. Hopefully you guys are very familiar with the vagus nerve, or you will be, to the medulla, and the medulla will send signals via the vagus nerve again to the cardiac muscle cells to lower the heart rate, get us back down to where we want to be. And then once we get the heart rate down, we stop this process. Example of the positive feedback, and there's just very few, and you will see this when we get to the reproductive system eventually. So again, I'm going to be very short with this. So the stimulus is baby wants out, all right? And so we have the amniotic sac break, the fetus drops, puts pressure on the uterus. We have stretch receptors in the uterine walls, and off we go to the hypothalamus again, and the hypothalamus will then work with the neurohypophysis, otherwise known as the what? What's the other name for neurohypophysis, somebody? Come on. Who knows the other name for the neurohypophysis? Nobody?
The posterior pituitary.
Outstanding, Diani. Very good. Very good. The posterior. So that's same thing. The posterior pituitary and neurohypophysis are the same thing. Good. And the neurohypophysis will release oxytocin. And that is a very powerful hormone that will get the smooth muscle in the uterus to contract, putting pressure on baby, causing more stretch, causing more release of oxytocin, and there's that positive feedback. We're going to keep doing that until finally we have a baby. And again, you're going to see this later on as well. And the reason you learn all this stuff is because what if it doesn't work? Because we're going to see a lot of examples of that. What if this natural process doesn't work and baby is just being stubborn? And you may have heard, well, several of you are parents, so you may have heard the term about inducing labor. And what do they really mean when they say we're going to induce labor? Anybody?
They inject oxytocin more.
Okay, or a version of synthetic oxytocin. Exactly right. Very good, Natalia. So yeah, it's one of those things where we know how the system works, so we can interfere with it. And so we give a mother that's just having very difficulty oxytocin to help, and hopefully that works. So that's why you learn this stuff, folks. Okay, we're going to change subjects here. Like I said, this is just a whirlwind of stuff. And you can see that's in green. And we're going to be talking a lot about diffusion in this course. A lot. So there's your definition. Okay. Christina says, didn't work for me either time. I had 2 emergency C-sections. Yeah. It doesn't work for everybody. You know, my daughter, she tried that too. It didn't work, so she had to have an emergency C-section as well. So yeah, it's not the cure-all, but that's what they'll try first before they do a C-section. But yep, understood. Thanks for sharing. Okay, so there it is, verbatim, folks, verbatim. And again, we're going to see this throughout this course in lots of different areas. And again, there should be a refresher. All right, so the net movement of substance from an area of high concentration to an area of low down its concentration gradient. So here's our very simplistic version. We're not interested in this type of diffusion because we're always going to involve a membrane. All right, so we have this membrane. Here we have a substance on one side and a substance on another. And so if it can pass through the membrane, it's going to diffuse across until we reach equilibrium. Equilibrium meaning I have equal numbers, so there's no more diffusion. So right here on this last square here, this isn't diffusion. This is just random movement. To have diffusion, I need to have, let me go back to this, net movement. Meaning I went from one area to another area and changed the concentration. Now, of great importance is to understand that every substance follows its own gradient, regardless of what's on the other side. So in this simple thing here, we have a lot of orange thingies on one, a lot of purple things on the other. They're both going to move in the direction from high concentration to low concentration until, again, they reach equilibrium. So our cells and our cell membranes are like highways, things going in and out based on their own gradients. This is a very important study slide, so put your stars next to this. All right, when we talk about passing through a membrane, we have some significant factors here. We have lipid solubility. Can it pass through a phospholipid bilayer? And again, that's something that you should know. So if it's lipid soluble, it can go through the phospholipids with no problem. So there are some things that we can't control. They're going to go from high to low regardless. And those, for us, are going to be things like our steroids, all right? Testosterone, estrogen, progesterone, cortisone, aldosterone, all those are lipid soluble, so they're going to pass right through a membrane. And many of those make up, obviously, those were all hormones that I just mentioned. The other important thing is size, all right? There are molecules that are just too big to get into the cell. And so I'm going to say this probably 10 times before your next test, but proteins are too big to pass through a cell membrane. There is no carrier, no channel, nothing that will allow a protein to get into a cell or out of a cell. I will need to do the old exocytosis or endocytosis. And I'll mention that briefly, but you should know what that is. So never forget that, because it's a very important concept that proteins don't go past the cell membrane. And you'll see why later on. So never forget that. Charge. Ions and polar molecules cannot go through the phospholipid bilayer. They need help in what we call facilitated transport. And so we will be talking a lot about carriers and channels in this course. So never forget, ions cannot go through the cell membrane, neither can polar molecules without a carrier or channel. So this is just kind of your little summary slide here. Okay, there are things that will use carriers, and I'll talk more about this, but things that are pretty large but not too big, like glucose, that's probably a great one to use. Glucose will use a carrier. If you're really small, like just sodium or potassium, you can use a channel. And again, the reason why glucose, somebody tell me, why wouldn't you have a channel for glucose? What would be the problem if you had a channel that was big enough for glucose to go through? Anyone? Well, it kind of needs to be regulated to some degree, but that's not why. Think about that. If you had a channel that was a channel, which is just a passageway that was big enough for glucose, what else would you expect to happen? And again, this is all about size. But we're going to keep this simple for right now. Somebody, why wouldn't I want this giant channel on my membrane? Well, that's okay. Those are extreme. Viruses and bacteria, those are huge. Okay, all I want to do to get at that is if you had a channel that big, then anything could go through, and you would have no control over any substance that was smaller than glucose. So the whole point of having a channel or a carrier is I can control that goes in. If I had a channel for glucose, then everything else could go in, and I don't want that to happen. We'll talk more about that later on. Oh, more green. And this is a big topic. We'll be talking about osmosis all the time in this course. It's big. So again, there's a definition, verbatim. So, and again, don't confuse this with diffusion. So you'll probably go back and forth, so you nail it and not confuse the two. Because when we talk about osmosis, we're talking about diffusion of just water and only water. All right, so that has to be in a definition. And water goes from an area of low solute concentration to an area of high solute concentration. So you'll have to work with that to make sure you understand that, okay? So once again, if I have, and I'm going to give you an example here in just a little bit, so this makes a whole lot of sense to you. So again, I'm going from an area that has low solute, and that solute could be anything, salt, glucose, you name it, to an area of high. And that's a huge dynamic in physiology. This should not be brand new to you. So when we talk about this, the water wants to be where the party is. You know, Jennifer, and that's good. That's the kind of the way I think, and I think I mentioned that to you guys last week, is try to come up with a story or something that works. So that's outstanding, Jennifer. That's outstanding. Very good. I like that kind of analogies. All right. So again, tonicity should not be a new concept to you. And again, it's all about water and which way water wants to go. And so we have these terms, tonicity, again, and this is a relative thing. It's a relative. We're talking about what's inside the cell versus what's outside the cell. And so if we have a hypertonic solution, that means there's more solutes outside the cell. And so water's going to want to leave. And so it will shrivel up. Hypotonic means there's less solute in the environment. So water is going to want to go in. And if it's a significant difference, that pressure of water going in can literally rupture cells. We call hemolysis in this example. So we want isotonic. So I'm going to take a little break here from my PowerPoint and go to my little, hopefully this will work, my little whiteboard. So hang tight, make sure. Okay, can everybody see this? Give me a, all right. So, because I think sometimes a visual is better if I do this, because there is going to be one very important parameter here. So I'm going to draw my, okay, all right, thank you, Derek. Okay, so here is my red blood cell. And the first thing that you're going to memorize for the first test is the normal concentration of sodium chloride in the cell. Does anybody know? Anybody know? Okay, this is a very important one. It'll be on your test. So 0.9%. 0.9% sodium chloride. I guess I can sneak that in there. Okay. Anybody know what we call that in a hospital? Okay, one little adjective with that, Christina. What kind of saline? It's isotonic, but usually they don't use that in the hospital. What do they call it? Anybody? Very good, Christina. Normal saline. Normal saline. So when you hear the term normal saline, they're telling you they have a concentration in an IV of 0.9%. So in our little drawing here, if I put the cell in a, pay attention, in a 0.1% solution, I got a problem, okay? Which way is water going to go, somebody? Does that make sense, what you just said? And that's why I'm doing this. Which one is the higher concentration? Yes, Jennifer.
Well, if the water wants to be where the solutes are, the party, wouldn't it, the water goes inside of the cell since you have less outside and you have more inside?
Exactly. And that's what I want everybody to remember that. So this is a, what do we call this? This solution is? Hypo, very good. Hypotonic. So water is going to go from low solute concentration to high solute concentration. And that would be significant enough where that red blood cell would be destroyed. Okay? So this is an important concept, all right? Because especially in your futures, for a lot of you, it's all about solute concentrations, making sure you have just the right amount of sodium, calcium, potassium, and watching out for these changes here. All right, and this is and now I'm going to give you a real world practical thing. I'd like to think everybody in this class right now knows that if you somehow found yourself out in the middle of the Gulf of Mexico on a raft Maybe you are out there and you fell asleep. Now you're in the middle of nowhere. What are you not going to do? Okay. I want to hear everybody say, do not drink the water. Okay? Because I don't care how thirsty you are. So here's my red blood cell, and I'm really thirsty. And remember, my black pens are all messed up, so I'm going to use blue here. So I'm at 9% here. Seawater is 10%. Exactly, Crystal. So 10% sodium chloride. So you drink this, folks, and what's going to happen? Which way is water going to go? Very good. It's going to go out. And then you know what happens? You die. Okay? You die really, really fast. Yes, they're going to be all looking like this. And that's just not red blood cells. This is going to be all your cells. So once your brain cells look like this, you're a goner. So you could probably live 3-4 days without water. If you drink seawater, you'd be dead within 12 hours. Okay? But now you know the actual physiology of why you don't do that. All right? And again, the first cells that are always affected is your brain. So your brain cells are going to look like that, and then they don't function, and then you'll go crazy. Okay. I have all kinds of cool little examples as we go through this course. Any questions? All right, we'll move on. Tell you what, let's take a 10-minute break. Well, no, let's go for another 20 minutes here. I'm still trying to work this new course because I've never worked a course with these strange hours that we have, and neither have any of you. So we'll work out our schedule here. Yes, Jennifer.
I think you mentioned it already, but I just want to make sure. So questions like this would be on the test, right?
Exactly.
Okay. I just want to know. Thank you.
Yeah, and I'm not going to do this every single time, but since it's brand new and we're just getting started, I might have a question that asks you to explain tonicity using a red blood cell and why, and what would happen if I had a solution of 5% sodium chloride. And then you're going to give me the answer. You're going to say, well, I know the sodium chloride solution in the cell, or concentration in the cell, is 0.9%. If I put it in a 5% solution, or 10, water is going to leave, crenate. So it'll be something like that. It'll probably start off the question, because some of the questions are 2 and 3 part. So I may start out with define homeostasis verbatim. Then, using the term tonicity, tell me what happens if I put a red blood cell in either one of these concentrations. Okay. Did somebody raise their hand? I saw for a second.
Yes, that was me, Professor.
Sure, Dana.
I was having trouble logging in initially. I was going to ask, would there be a recorded version of this in case?
No, I don't do that.
Oh my God. Okay.
But okay, class, what is he going to do if he has problems? Come on, guys, teamwork. What's he going to do? All right. Ask GroupMe. Very good. All right, you guys are on top of this. You guys are really on top of this. All right.
Thank you so much.
So, and again, the group will tell you why I don't record these, because like I've learned from past experiences, if people think it's recorded, they don't even bother showing up. And I want to interact with the group. That's what the only fun thing about teaching is interacting with your students. So
Thank you.
I want you to be in class, but your class got your back. Okay.
Thank you so much.
All right. So let's go back to our PowerPoints. And all right. So again, we gears here because I'm just trying to cover the really, really important things. So we're back to facilitated diffusion. So again, I use channels for really small things like ions. I use carriers for larger things like glucose and amino acids, okay, that are too big to pass through a channel. We're going to look at all kinds of these carriers and channels in this course. Active transport, you should be familiar with that. By far the most important active transport pump is the sodium-potassium pump. Now, don't sit here and try to study all this stuff. All you have to do is tell me the sodium-potassium pump pumps 3 sodiums out and 2 potassiums in. Never forget that. Say that to yourself 50 times till it makes sense. And we'll see just how super important the sodium-potassium pump is in several future lectures. Coupled transport usually uses the sodium-potassium pump. So I'm pumping sodium out, typically, of the cell. Sodium wants to come back through diffusion. So it will find what's called a co-transporter. Sodium will go through this, and because this is energy, sort of like water behind a dam, the sodium comes in and it pulls something else against its gradient. And this little setup is basically what happens in the heart. So you'll see this again. But a co-transport typically uses a sodium-potassium pump, and sodium is going to pull another product in against its gradient, against. All right. You'll see this in several situations here. Okay, cell communication, homeostasis is all about cell communication. So the only ones that we're truly, really concerned with right now is the neurotransmitter business, which you all know, or you should know from AMP1. And then something you probably didn't get a whole lot of is the endocrine system. And the endocrine, which always scares a lot of people, endocrine just means I am going to dump a chemical signal into the bloodstream. And that chemical signal that's in the bloodstream is called a hormone. A hormone is a very, very generic word. There are dozens and dozens and dozens of things called hormones. You're going to learn a lot of them. But it's called a hormone because it's in the bloodstream. To give you an example of the difference, you will learn more about epinephrine in this course than you ever have before. But epinephrine can be released by a neuron, and we call it a neurotransmitter. But the adrenal medulla also releases epinephrine into the bloodstream, so now it's called a hormone. So again, hormone just means it's in the bloodstream. And you're going to learn in this course, there's all kinds of signaling that we're going to talk about. So I'm not going to spend too much time with that because you're going to learn all those in the endocrine lecture. Again, if the chemical signal is lipid soluble, and here you have a couple different names for the same thing. So lipid soluble means the same thing as a nonpolar or a fat, or you can even flip it and say, instead of lipophilic, you can say hydrophobic. So when we get to the endocrine system, we'll go over the terminology because there's several different ways to say something can go through the phospholipid bilayer and other things can't. So we'll keep it simple. So lipophilic or nonpolar or lipid soluble will go right through the phospholipid bilayer and bind to a receptor inside the cell. We're basically talking about steroids here. If you are lipophobic or hydrophilic, or you're polar, you need to bind to a receptor on the membrane. And so we have 3 basic types of receptors, or ligands as we call them. Okay, We got a question. Oh, okay. So Jessica just put something in there. Great. Thank you, Jessica. All right. So we have a basic ligand-gated channel. It just opens and closes. We have enzyme receptors and G protein receptors. And you're going to see all three of these throughout AMP2 on a regular basis. So a chemically gated channel, very simple. Signal of any kind binds, the gate opens, and something rushes in. And again, this is where the diffusion comes in. So if I open this channel and things go into the cell, then you know there was a higher concentration outside the cell than was inside the cell. The other is an enzyme receptor. And again, the signal molecule binds to it. Hopefully everybody knows what an enzyme is in this course. What's the fastest, quickest definition? Somebody tell me what an enzyme is. Come on. Okay, Christine, that's good. Come on, folks. I got like 5, 6, 7 of you that are participating, and the other 10 are just kind of like going along for a ride. Jump in. So, very good, Christine. It speeds up reactions. And we'll talk more about enzymes later on. The most important enzyme I want you to know in this course are called protein kinases. And we'll talk more about this later, but a kinase is an enzyme because it ends in ase. I'd like to think everybody knows that. A kinase is an enzyme that activates another protein. It activates a protein by giving it a phosphate that it got from ATP. So if you look down here at our illustration, here's my ATP, here's my kinase. I pluck off one of the phosphates, give it to the protein. Now that protein is activated. I mean, it's going to do whatever its job is to do. And let's ask another question that doesn't involve Christine. All right. What determines an enzyme's function? Somebody.
Temperature or like pH.
Okay, that's good. The temperature and pH, but what does the temperature and pH do? Very good, Jennifer. Very good. So yeah, the buccal, temperature and pH, but what they did is it changed its shape. So once again, the simple answer is a protein's function is determined by its shape. And so when you add a phosphate to a protein, it changes its shape, and now it does what it's supposed to do. This is the one I want you to know because we're going to use this as our big example, and that is what's called a tyrosine kinase, RTK, tyrosine kinase. All right. Now, you don't have to study any of these illustrations down there. I'm not going to ask you anything about that. What I do want you to know is one of our classic case studies in this class is going to be about glucose regulation, insulin, diabetes. So you need to know right now simply that the receptor on your cell that will trigger the formation of glucose transporters is a tyrosine kinase. All right. Now this will make a little bit more sense, so don't freak out if you're like, what in the world is he talking about? I'm saying that if every one of your cells in your cell bodies have these RTKs, and when you have high levels of glucose, the pancreas is going to release insulin. Insulin is going to bind to that tyrosine kinase and tell the cell to make transporters to bring the glucose into the cell so I can make ATP. We'll see more examples of that later. Okay, so again, this is just a quick review. I'm going to fly through this. This is not that important, but again, our normal process is I have a receptor, I have a transduction, which could involve several enzymes, intermediates before I eventually have a response. And we're going to see lots of different examples. So again, we have second messengers, which means I have the initial signal response to a receptor that initiates some sort of signal transduction that can do all kinds of different things. There's my protein kinases, which phosphorylate proteins. I could have a second enzyme involved, and that enzyme is creating second messengers that can do all kinds of different things. We're going to see lots of examples in this course involving that. The two that you need to know right off the bat is our cyclic AMP messenger and our IP3. So this is going to be another study question right away. So I have a signal. It binds to what is called a G protein linked receptor. That receptor is going to activate what is called a G protein. The G protein is going to activate an enzyme called adenylyl cyclase. You can also say adenylate cyclase. That is going to take ATP, take two phosphates away, so now it is AMP. So this is adenosine triphosphate. We're going to make something called adenosine monophosphate, and we're going to change its shape a little bit so it gets the name cyclic AMP. Cyclic AMP is a second messenger that's going to activate a protein kinase. And then notice how it says A there. That's because there's dozens and dozens of different protein kinases, and ultimately I get a response. So this picture here is just to give you a visualization here. So here's my ATP. I have three phosphates, 1, 2, 3. The adenylyl cyclase plucks off two phosphates, then wraps the last phosphate around, ergo the name cyclic, and now this is a very powerful cell signal inside the cell. When I'm done with whatever that response was supposed to be, I want to deactivate cyclic AMP. So I use something called phosphodiesterase, commonly known as just PDE. And if you notice, all I do is unhook the phosphate. So it's no longer cyclic, it's just AMP. And then it's just going to find its way to get some more phosphates hooked up to it. So we use this. We use this for a lot of things in science, folks. I'm going to give you a little quick story. It's humorous. I think you'll like it. Yeah. Okay, so this is your cute little story. So this cyclic AMP does a lot of different things for a lot of different tissues, for a lot of different organs. It's like I said, it's an internal cellular messenger. Excuse me. In your blood vessels, in your arteries, cyclic AMP causes vasodilation. So cyclic AMP causes your arteries to dilate. Well, as you're going to learn in a couple of weeks, is one way to get your blood pressure lower is to have your blood vessels dilate so the volume is increased. There's an inverse relationship. So I increase the volume, I decrease the pressure. Everybody with me so far? Okay. So, and of course, as you all know, one of the biggest problems in this country is high blood pressure. So all the researchers, scientists, pharmaceutical folks were looking for drugs that would cause vasodilation and sell it as a hypertension medicine to lower blood pressure. Okay, everybody with me so far? Because it gets crazier from here. So what they figured they would do is, if we can block phosphodiesterase, remember, phosphodiesterase is the enzyme that's going to deactivate the cyclic AMP. So this doesn't do anything. So the scientists said, hey, if we can knock this stuff out, if we can stop this phosphodiesterase, then we can keep the cyclic AMP going and keep the blood vessels dilated and lower the blood pressure. So there's a couple different drugs that knock this enzyme out. So it does not allow cyclic AMP to be inactivated into AMP. So they gave it to a whole bunch of people, subjects. And midway through the research study, the guys were coming back and saying, Doc, I don't know about my blood pressure, but something else is working pretty darn well. Anybody want to guess? Andy, what am I talking about? Very good. Very good. Yes, Andy. Yes. So, yeah, that's how it works sometimes, serendipitous type of things. So, yeah, so Viagra and Cialis were initially for the purpose of lowering blood pressure. But as soon as they saw what other uses it had, they quickly shifted to where the money is. And that's a true story. Okay, fun with science. Yep. All right. So again, when we have these second messenger systems, the big thing, and you might want to just put a star right here because you're going to make sure you tell me this is all about amplifying the process. I want a cascade of events so that I make a lot of product or I have a huge cell response. So if I have several enzymes involved, I can, again, amplify what I want. And remember, one of the characteristics of an enzyme, it can do the same thing over and over and over again, right? So don't let this slide scare you. There's nothing on here that you need to know. I just want to show you what we mean by amplification. So if you have a fight or flight response, i.e. a sympathetic response, you're going to produce a bunch of epinephrine. And one of the things we want is plenty of glucose to make plenty of ATP so I can either fight the bear or run away from the bear. All right. So one molecule of epinephrine binds to a G protein. And look at these cascade of events, all right? Because each time I activate an enzyme, it can activate another enzyme and activate another enzyme, and on and on and on. Ultimately, and that's all I want you to see or appreciate of this cascading thing with different enzymes, is one molecule of epinephrine causes the cell to produce 100 million molecules of glucose. And that's one cell, 100 million molecules of glucose. That is amplification from 1 to 100 million. But again, none of this is testable, just this. All right, the other second messenger system, not quite as common as a cyclic AMP. And folks, to tell you diversity, let me go back up here. This is this receptor that you use for everything from speeding up and slowing down your heart to your sense of smell. So, like I said, there are hundreds of different types of cyclic AMP second messenger G protein systems for a vast array of different cell responses. If we even your sense of taste is a second messenger G protein system, and you're going to learn those if you didn't in AMP1 under special senses. Okay, so the other one, a little more complicated, but don't let this scare you. Just get the basics. So the big thing here is our first messenger binds to a G protein link receptor, activates a G protein, and here are the enzyme changes. So instead of adenocyclase, we have phospholipase C. And again, you see the phospholip in there. So what it does, simply don't worry about any of this chemical molecular stuff. This phospholipase C takes the phospholipid and turns it into something that we call IP3. That stands for inositol triphosphate. You don't need to know that. It's IP3. IP3 is a second messenger that goes and binds to a receptor, a gate, channel on your ER. And what you should have learned way back when is your endoplasmic reticulum, one of its main functions is to store calcium. So the IP3 is a chemical signal that opens up a calcium-gated channel here. Calcium rushes out, and then it can do a bunch of things. And you're going to learn about all those bunch of things later on. Any questions? All right, then. All right, a lot of stuff. Next is neurophysiology, and then we're almost done here, folks. Not too much more. And again, this should all be a refresher. So again, I'm not going to go through all this, but we're going to be using that diffusion word quite a bit. So again, review this. I shouldn't have to. Okay, but for, again, you're going to see this a lot. And all you have to tell me, folks, 3 sodium out, 2 potassium in. In fact, I'm going to do this one more time. Here we go. Because it's so important. So I'm going to go to my little whiteboard here. All right, so I'm going to draw a cell. It doesn't matter what kind of cell. You can use your imagination. I don't care. It's just a cell. I'll mark it as a cell. And then I have my sodium-potassium pump. And this isn't meant to be a trick question. So here's my sodium-potassium pump. And I just emphasize that it's going to pump how many sodiums out? Quick. All right, beautiful. That's what I want to see. I want to see a lot of responses. Beautiful. Let's have fun with this. All right. And I'm going to pump how many potassiums in? 2. Beautiful. So here's your question. I love the responses. Very cool. All right. So here is the responses. Should be a simple question, but oh my gosh, you got to learn this. You got to learn this because you're going to see this so often throughout this course. So if I have a channel and I open it and it's a sodium channel, that's my sodium channel. Which way is sodium going to go? Okay. All right. And that's why I decided to do this. All right. Okay, folks, come on. Think about it. Oops, let me move this here. If I'm pumping sodium out, sodium is going to be higher than the outside. And I don't know if your AMP1 teacher taught you this, but we use a bracket to tell you concentration. That references concentration. So it's high out here, sodium, and maybe this is just what you needed to help you. And the concentration of potassium is high inside. So one more time, which way is sodium going to go? Because we have a half and half here.
Inside?
Cherise says inside. Amy, why do you say outside? What's diffusion tell us? Nada, explain to her. Autumn, you guys, you're right, but we want to make sure everybody.
From a higher concentration to a lower concentration?
That's exactly right. Every single time. This is an important concept. We can see it over and over and over again. All right. if I have a potassium channel and I open it up, which way is potassium going to go? Okay. Are you sure, Christina? Are you positive? Okay, good answer. Don't let me psych you out. All right, that's good. It's gonna go out. Folks, this is gonna be on your test. It's gonna be on your test, and you should have learned this in AMP1, but we're gonna be using it all throughout. So never forget that. You know, I'll take a picture of it right now, please. Take a screenshot of this thing. All right. I just wanted to emphasize that. Everybody take a screenshot because I'm going to go back to our thing. Okay. Great. Beautiful. All right. So I introduced that because you learned all of this in AMP1, but like I said, I don't know if you retained much or if your instructor covered it to the extent that he did. But this whole business of sodium, potassium is all about our. Gosh, I don't know why I'm a stupid. Hold on, give me a second. There you go. Okay, so again, we're going to be. You're going to relearn action potentials, because in this course you're going to have to learn cardiac action potentials, all kinds of different other action potentials. So this is a quick review of what you should have already learned. So this is important. So again, remember, resting membrane potential is minus 70 millivolts. Okay, and so if we took a voltmeter and we measured it, it would say minus 7. Remember, the minus doesn't mean less than 0. It just means the charge is negative versus positive. All right. So, and again, I don't know if, oh, what the heck. Let me go back. I just want to make sure you guys can grasp this stuff. So I'm going to go back to my camera. All right. Because it's important. So, and we can have a little bit of fun. So that resting membrane potential, where'd the word potential come from? Can somebody tell me? What are we referring to when we say potential? Anybody? Nope, not a gradient.
With rest.
What do? Oh. Well, that's what potential means. Okay, and that's fine. When we talk about, yes, Jennifer.
Does it take back all the way from like kinetic energy and potential energy, something like that?
Yes, it does. You just nailed it. Very good. You nailed it. Yes. The word potential comes from potential energy. Potential energy. So that's exactly what I was looking for. Beautiful. So let me give you an example. All right. That's just fun. So we still use batteries, AA's and AAA's, for our remote controls and all that kind of stuff. Boom, 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 boom. And we have a positive side and a negative side. Okay. Now here's a question that if you were anywhere close to my age, you would know. Yes, and that's a battery. No laughing. All right. You would know how many volts that is. Can anybody tell me how many volts in your AA, AAA, B, C? They're all the same.
I think it's 1.5.
Who said that? Diani?
Yeah.
You get a gold. You get a gold star. You get a gold star. Maybe 1 in 100 people know that. So yeah. So the typical battery is 1.5 volts. All right. And so if I were to measure this with my voltmeter, so here's my meter that measures volts, and I'm just going to do a quick little thing here. Okay, boom, boom, boom. This gives you a chance to. So there's my voltmeter, and then I put electrode on this end, an electrode on this end, and my voltmeter is going to say 1.5 volts. That's potential energy, folks. That's potential energy. I need to connect these two ends to a source, whether it's remote control or whatever device. And then I went from potential energy to kinetic energy, like Deani said. So that's where the word resting membrane potential energy. So this is 1.5 volts. All right. And this is what we're going to talk about on Wednesday, because you have to know it. Who can impress the daylights out of me and tell me how many millivolts 1.5 volts is? And Christine gets the prize. It's 1,500 volts. And that's going to be kind of like the metric questions you're going to get in my tests. And we'll talk about that. But you need to know that relationship. Okay? And I really emphasize that really, really hard. You guys will learn the metric system in this course, or you will not be able to get an A. I was going to say that for Wednesday, but I'm going to tell you right now, 10% of every exam you have in my class are metric questions, very similar to this. All right? So if you refuse to learn the metric system, you won't be able to get an A in my class. All right? And I said, I'll make a big deal of this later, but you folks have chosen careers where the metric system is what we use for science and medicine. All right. All your dosing is metric, and all your physiological parameters are metric. You must know the metric system. And I'll make a big deal. Anyway, so my point with this is, so your average little, AA, AAA battery is 1,500 millivolts potential energy. Getting back to our cell, it's 70 millivolts. Okay. And again, that negative just means it's a negative charge. All right. I hope that helped a little bit. Does that make sense to most people now? All right, good. All right. So we'll go back to our presentation. So this is all this is saying is if I put my voltmeter like I just showed you here, I'd have a 70 millivolt potential energy, resting membrane potential. All right, and I'm not going to make a big deal. There's our sodium potassium pump. And so when all is said and done, and I'm not going to make a big deal about you learning anything about moles and millimoles and things, but suffice it to say there's a bunch of sodium outside, which is why I just went through that process. There's potassium inside. Sodium is positive. Inside the cell, which is kind of important, what makes the inside negative is the fact, you see this little tiny thing that says AA negative? That's referring to proteins. Proteins are typically negatively charged. And what did I say about proteins just a little while ago? Who's been paying attention? Excellent. Okay. All right. You guys are awesome. Yes. They're too big. So they are never leaving. So they stay in the cell and they keep the inside negative. Beautiful. Beautiful. All right. But don't worry about these other numbers. I'm not going to ask you what the millimolar concentration of sodium is, anything like that. So we have this potential energy where sodium wants to go in, potassium wants to go out. Never forget that. And so we have channels that can control when sodium goes in and when sodium goes out. And the same thing with potassium. So again, mechanical, chemical, and voltage gated channels. We're going to look at lots of these in this course, and I really hope this isn't the first time you're hearing this stuff. Okay, so when we talk about a graded potential, we're talking about a little change in our membrane potential. Remember, resting it's minus 70. But if I give it a stimulus, all right, here we got a little red hot poker, I guess, but it could be physical, chemical, and I open some channels, sodium channels. Sodium comes in. I have what we call a depolarizing event. And break that word down. Remember what polar can mean. It means positive on one side and negative on the other. That's what polar means. So when I depolarize something, I'm changing that positive to negative across the membrane. All right? So we have this little depolarizing event. But if it's a weak one, it's going to fade away. All right? And here's stuff that you'll want to study for your test. Okay? So graded potential is a stimulus that kind of got the neuron excited, the receptor excited, but it wasn't strong. So the depolarizing event just fizzled out like it never happened. That's called a graded potential. So here, and again, don't let all this stuff scare you. So it's just saying here, I got a stimulus. It could be from another neuron, could be from external energy, but it was weak. So by the time that depolarizing event that we just talked about gets to a critical area, how many remember the axon hillock in AMP1? This area right here. So in anatomy, this area is called the axon hillock. In physiology, it's called the trigger zone, which is way cooler name, don't you think? All right. So we have the trigger zone. That's where the action happens. So if my depolarizing event, by the time it gets to the trigger zone, and look where the electrode says, oh, geez, I'm below threshold. And I probably should have emphasized that, but you guys should know that. Your threshold for a neuron is 55 millivolts, meaning I start at 70, minus 70, and I got to get to minus 55 to trigger an action potential. So on this side over here, by the time the depolarizing event got to the trigger zone, it was below threshold, so it just fades away, as it shows right here. If I have a strong stimulus, so the depolarizing event gets to the trigger zone, I'm over here still above minus 55, so boom, I have an action potential, and I'm on my way to sending a cell signal. All right. Time to think. Why would we ever have, and somebody besides Christine and the handful of others talk to me, why would we even have a graded potential? Why would you have this little deep, but it just fizzled out? Why are these graded potentials even exist? Or if I turn the question, why would it be bad if every stimulus created an action potential? So you guys have to think in this course. Come on, somebody. Okay, well, that could be, Sarish. Could be. But I'm looking at the really bigger picture. Bigger. Why wouldn't you want to have action potentials for every little stimulus that you got? Somebody, come on, some of you folks that haven't been talking much. No, this has nothing to do. No, ATP, no. We're missing the big picture. You guys are in the weeds.
would cause just different reactions, brain wires.
Well, you're kind of you're doing good, Nina. Let me put it another way. Do you want to feel every?
It is for us. It is for us to function well.
Okay. All right. Well, Daniel just nailed it. Would you really want to feel every little piece of dust that landed on your arm? Would you? No. Your brain would just be overwhelmed with information. So think about that in your everyday life. There's a lot of stimuli out there that you're not aware of because it didn't register an action potential and send it to your brain because you'd be overwhelmed. Yeah, you'd go crazy. You'd go crazy. Yeah. That would be a hard life, Samantha. You're right. That would suck to have to feel every tiny little thing going on out there. Christina, you're crazy. Okay. All right. So I just wanted you to understand why we want a strong stimulus because we don't want to fill our brain with silly stuff that it doesn't need to know about. It doesn't need to know about the dust on your skin. All right. So action potential is all or none. We have to get that magic minus 55 millivolts. And then, boom, we have our action potential. And again, this is stuff that it should have been covered, but that's why I do this refresher. All right. So all or none, either happens or it doesn't. And so there's your basic little, and you can look at things. But folks, I need you. This is going to be another test question. All right. So who's keeping tally? Andy, how many test questions have you noticed that you jotted down that you know is going to be on the test?
Several. Positive feedback, negative feedback. You said homeostasis, osmosis.
Well, that's what I want to hear. And folks, this is how this course is going to run. So I would like to think, if you haven't, you start. But I'd like to think many of you have sat down there, and every time I said this is going to be on the test, you made a note. So, again, you made it green. Okay, that's good, Christina. Cindy has 18 so far. All right, that's good. See, Cindy pretty much has a whole test already in her hands. Highlighting as we go, but there are on several occasions, I said this is going to be on the test. I literally said that out loud. So if you're writing and you're paying attention, you know where to get a head start. Okay, good. So this is going to be on a test. You need to know this. And so what you will see on the test is this graph, this curve, and all these letters and words are going to be blank. And you're going to fill it in. Does everybody get that? So this is one of your big essay questions. You're going to get the curve, just the curve, and everything else will be erased, and you're going to fill it in. And I'd like to think, yeah, it's fun. It's fun. It's a game, This should be the game when you go to McDonald's and they're waiting for your food, and you just put this, fill it out. Anyway, yeah. You make your kids, instead of giving those silly little maze games, you give your kids a graph of action potential. All right, so remember what this is, what we're looking at. This is a snapshot of electrodes monitoring an action potential as it goes by. All right, it's like, if you saw a car going by and you took a photograph of it. So let's walk this through. And again, I hope this is a refresher. So here we are, where everything's cool. I'm sitting at minus 70. Nothing's happened. Ooh, I got a stimulus. And I opened some sodium channels. And they could, like I said, they could be mechanical, they could be electrical, they could be, chemical. Something opened some sodium channels. And enough of these sodium channels opened to, boom, get me to minus 55. And the way I want you to think about this, folks, is think what's going on here. I'm having these channels open. Sodium is rushing in. Sodium is positive. So the more positives come in, the less negative I get. So sodium comes in. I'm less negative. I'm now at 55, the magic number. And now a different channel opens. And we'll talk about these in detail later. But these are all electrical channels, or voltage-gated channels, as we say. These channels on the membrane open at minus 55. So you have a whole bunch of channels opening at minus 55, a bunch of sodium coming in. I have an action potential, and sodium rushes in. I'm depolarizing, and boom, I max out at around plus 30. The sodium channels say, I did my job. And so they close at plus 30. So you have channels that open at minus 55 and close at plus 30. And they're done. They did their job. The potassium channels open at plus 30. And as I went over and over again, if I open a potassium channel, which way does potassium go? I want everybody right now, tell me, which way is potassium going to go when I open a potassium channel? All right. Well, I would rather have seen 20 outs, but that'll work. Okay. And since potassium is also positive, as potassium leaves, I get less positive inside. So I'm repolarizing. Potassium is leaving and leaving. That's what efflux means. Leaving and leaving. Oh, shoot. Oh, God, those potassium channels stayed open kind of a little bit too long. So I'm now hyperpolarized, meaning I started at minus 70, but now I'm probably around 80, 85.
Negative.
Huh?
Negative, right?
Negative, yeah, not negative 80, 85, 90, depending on the cell, and we're all just remember, this is biology, so we're all a little bit different. So we'll say between 80 and 90, but I'm definitely below where I'm supposed to be at minus 70. All right, so I'm negative 90, negative 80. The potassium channels finally close, thank goodness. And what gets me back to minus 70? Our friend, the sodium potassium pump. Okay, so that sodium potassium pump will get me back to where I need to be with more sodium on the outside and more potassium on the inside. All right. This is really important, folks. Oh, I cannot emphasize this enough. And this is just my little, how many times are you going to see this? A lot. But my point is it's not good enough that you understand how an action potential works. In my class, you need to be able to explain this and then tell me what happens if everything isn't just right. So what do I mean by that? All right, so I'm looking at who's really participating, and I might just pick somebody I haven't heard from in a while. Okay, I'm just going to randomly pick Autumn. Autumn, you with me? And again, I know some of you do that because I'll be honest, on some of the boring meetings I have to, I'll log in so it looks like I'm there, but I'm not. But you guys should make a habit of that. So who else do I pick that I haven't heard from much? Joshua. You with me, Joshua?
Yes, sir.
Okay, Joshua. So you get to be the first guinea pig here. So Joshua, you're looking at this. You know which way sodium's supposed to go. Which way. So Joshua, what's going to happen if I have a patient that has way too much potassium outside the cell than they should have. All right. So that we call this hyper for high kalemia. Kalemia. Meaning your potassium levels are too high compared to what they should be. You with me so far, Joshua?
Yes, sir.
Okay. Okay, so Joshua, if I have these high levels of potassium outside the cell, how is it going to affect my action potential?
I mean, I would say that it's obviously going to cause the potassium to not exit the cell, so it would shut down the action potential.
Okay, I will give you 1.5 stars for that answer, maybe even two stars for that answer. But you definitely did a great job on answering that. So, and I'd like to think all of you are following the same line of thinking that Joshua is. If there's a bunch of potassium outside, when I open those potassium channels, the potassium doesn't really want to leave. Remember what we talked about diffusion. This is all diffusion. I'm going from high concentration to low. If my potassium levels aren't that low, the potassium isn't going to leave. Does everybody get that? I mean, again, envision that. Here's all my potassium. My potassium is so excited. It is ready to charge out if that gate opens. And that gate opens, and oh my gosh, there's already a bunch of potassium out there. You know? I don't remember who was that used the analogy about the party, but it'd be like, okay, I open the door to go to party, and there's already thousands of people in the party. And I'm like, frick. Yeah. Okay, Jennifer. So hopefully you can see that. So I open the door to go to the party, and there's already a bunch of people in there, and they're all wearing the same outfit I am. You don't want to go there. So potassium doesn't want to leave. And so Josh was correct that it's going to shut down because my repolarizing event isn't really going to happen very well. If it's not too bad, all I'm going to do is extend the time it takes to repolarize, because it's just slowly leaving, so I can stretch this out. Does everybody follow where I'm going with this? Because this happens, folks. When you get into your future jobs as nurses, they're going to be students. You're going to have patients that are going to have bad kidneys, and that will make more sense when we get to the renal system. That they're not regulating sodium and potassium, so you could have too much potassium or too little sodium. And that would be the opposite of that. If I had low sodium levels, how is that going to affect me? And okay, so Joshua did a great job, so I'm going to pick on somebody else. Derek, you with me?
Yes, I'm here.
Okay, so Derek, if I have low sodium, yeah, and we'll talk about that, Andrea. We'll talk about those things in the kidneys with dogs and everything, because I'm into that too. So Derek, my sodium levels are low. That's called hypo for low, natremia. So how is that going to affect my action potential? If I open sodium channels, what's my problem?
If it is low, then that means there will be more sodium coming in.
No, really? So if my sodium levels are low outside, more is going to go in? Does that follow the rule of diffusion?
So it's from a lower concentration to a higher concentration?
No, that's not the definition of diffusion. Diffusion says I go from high concentration to low concentration. And I just told you the sodium levels are low outside. So does sodium want to go into the cell?
No, they will go outside, yes, per the definition.
All right, well, it wouldn't go outside, it just wouldn't go in. All right, if it was that low, you'd be dead already. All right. So again, I'm trying to get you guys to understand that this is all about gradients, because this is a real thing in your futures. Is if you have a patient with low sodium levels, that's dangerous because they may never be able to get to threshold because not a whole lot of sodium is going in like it should. And it's just as dangerous if potassium levels are too high, because potassium won't want to leave the cell to repolarize. Does everybody follow me?
So, Sarah, what's the answer to that?
The answer is if your sodium levels are too low outside the cell does not want to depolarize because not a lot is going in, so it may not get to minus 55.
Okay.
Okay? So again, remember the definition of diffusion, high to low. If I have low to low, then I have no diffusion. I have no depolarizing event. All right. Okay, so you guys want to hear the morbid part of this lecture? Oh, yeah. So this may be news to you, but when the government decides they need to execute somebody, they give them a series of drugs to basically put them into a la-la land where they don't feel anything. But you know what the last injection they get that actually kills that individual? They give them a bunch of, look at the chart. If I want to mess everything up, what's the last thing that will finish off this individual? I shouldn't say finish off, but actually, no one knows? Very good, Christina. Very good, Cindy Sarish. Yeah. The last shot an individual gets is a whole high dose of potassium. That's it. It's that simple. You load somebody up with potassium, they can't repolarize, and then Daniel, you have to eat a whole lot of bananas. You have to eat a whole lot of bananas to give you the amount that they give somebody they're going to execute. So yeah, so now you know. That was a good one, Daniel. I like that. All right. Enough of the morbid stuff, but yeah, all the other drugs they give them are just like to just anesthetize or just knock them out a little bit. So now you know. All right, so we're going to move along here. 400 bananas. Okay, I'm sure Andrea did all the research on that to get the right dosage. So if you want to off somebody, try to get them to eat 400 bananas. All right. That's why I don't record these lectures, not to give you any ideas. All right. So we're going to wrap this up here. We're almost done. And this is the kind of a slide that tells you, and again, potassium is very critical. And we're going to talk more about potassium when we talk about the heart as well. All right, wrapping up. We're trying to move this along here. We're doing good. We're doing good on time. So again, this is to be review. So the whole purpose of an action potential is to communicate to the next cell. So once that action potential reaches the axon terminal, all right, and of course that has several different names in anatomy, bouton, knob, button, whatever. In physiology, we just call it the axon terminal. It's the end here, all right? And so we have just a couple other things going on. So when that action potential reaches the axon terminal, and we have some terms I want you to be familiar with. The axon terminal we call the presynaptic membrane, and the target cell is called the postsynaptic membrane. All right. So when that action potential gets down there, remember action potential is at plus 30 millivolts. And now there's another voltage gated channel. It's a calcium channel. and it opens at plus 30 millivolts. So when that action potential gets down there, the calcium channels open, calcium rushes in, and that's another thing that you need to make a mental note of. Calcium is always higher outside the cell. So if I open a calcium channel, calcium is going to rush in. Now, calcium, we kind of mentioned it a little bit before, is a second messenger. All right. So it's way beyond the level of this course, other than to say when calcium rushes in, magic happens and causes these synaptic vesicles to migrate to the presynaptic membrane and release the neurotransmitter through exocytosis. That neurotransmitter will bind to a receptor on the target cell and trigger the target cell to do whatever it's supposed to do. So once again, there's conditions that are like hypocalcemia, low calcium levels. And I'd like you to follow the reasoning. If I have low calcium levels, when I open calcium channels, not a whole lot of calcium comes in, so not a whole lot of transmitter is ultimately released. Does that make sense to everybody? All right, that's what I want to hear. So that could be a very big problem. If you're hypocalcemic, low calcium levels, you may not be able to release enough neurotransmitter for things to respond like they should. All right. Beautiful. All right. And then, of course, when everything is done, I've contacted the target cell. The target cell is going to do what it's supposed to do. And now I need to shut this down so, I'm not constantly stimulating the target cell once it's already knows what it's supposed to do. So I have to get rid of that neurotransmitter. So some of it will just diffuse out, good old diffusion from high to low. Oftentimes, the postsynaptic membrane, the target cell, will have an enzyme that will break down the neurotransmitter so it's no longer inactive. That happens in your muscle cells. Who can impress me and tell me what is the neurotransmitter that excites a skeletal muscle cell? Very good, Sadish. Yeah, very good. Acetylcholine. And so on the skeletal muscle cell, you will have what is called acetylcholine esterase. And its job is to break down the acetylcholine so that muscle cell can relax when it's time for it to relax. And some of it will be taken back in and recycled. All right, what we call reuptake, to be used again. So here's your next practical example of why you're learning this stuff. So who knows what a SSRI is? Not quite anxiety.
Increases serotonin.
All right, you're all kind of hedging around, but why do we give somebody that has? Why do we give somebody SSRI?
Well, I know that there's multiple reasons for that medication. It can be antidepressant, or it can also help stimulate the gut movement.
Yeah, and Andy, that's a great thing, and you're going to learn this in the course. There's, believe it or not, as complex as humans are, we don't have that many hormones or neurotransmitters. So serotonin in your digestive system is a hormone. In the nervous system, it has many roles, but one of them, and some of you put that in there, is serotonin is considered your happy neurotransmitter. All right, satisfying your habitual whatever desires and whatnot. So we give SSRIs to people that have depression, as Deani and Christina have said in there. And the whole purpose is, and it's called selective because we only want it to work on these particular type of cells. Because like I said, serotonin has several different functions. So we target these cells that say, hey, we don't want you to uptake the serotonin. We want the serotonin to stay in there and keep doing what it's doing. So selective serotonin reuptake inhibitor. We are not going to let it uptake the serotonin. Serotonin will stay in there and hopefully keep the patient from falling into depression. So now you know. All right, beautiful. Okay, wrapping this up. As I said before, oftentimes a stimulus isn't strong enough to get me to threshold. It's a graded potential. So we have what's called EPSPs and IPSPs, graded depolarizations, meaning, okay, I had a little bit of stimulus, and I want to emphasize this, rarely can one neuron get the second neuron to reach threshold with one synapse, all right? So typically, we have what's called the EPSP, excitatory postsynaptic potential, meaning I depolarized it, but didn't give me the threshold, so it went away. I also have IPSPs, where I'm trying to inhibit something. I don't want something to happen, meaning I want it to be less negative, or excuse me, more negative, so it's hyperpolarized. So those are your two types of graded potentials, and we'll explain more of that later on. All right, don't let any of this scare you. I just want you to recognize these these are the most prominent neurotransmitters in your body. And like I said, they have so many different functions. So I just want you to recognize these as neurotransmitters because they're going to pop up throughout this course. And most of them can be either excitatory or inhibitory depending on the target cell. So for instance, a simple example is acetylcholine. That gets your muscles, your skeletal muscles, to contract. It's excitatory. However, that same neurotransmitter actually inhibits your heart and slows it down. And you'll learn exactly how it does that later on. Same thing with epinephrine and norepinephrine. They can excite some things, like it'll speed up your heart, but at the same time, it can slow down your digestive system. So just recognize these as neurotransmitters. And again, how do we excite? How do we inhibit? It's all about, am I farther away from threshold or closer to threshold? All right, so glutamate is excitatory because it opens up those sodium channels. GABA is inhibitory because it opens up chloride channels. And remember that little thing too. Your sodium came because you ate salt, which is sodium chloride. So wherever sodium is, chloride's right there. So chloride is also higher outside the cell. So if you open a chloride channel, it's negative, it's going to rush in and get you farther away from threshold. And then you have your second messenger systems that can do all kinds of cool things that you're going to learn. All right? So how do I get my second cell to get to threshold? Summation, meaning I have a little like a staircase to threshold. Two ways to do that. Temporal, which means the same neuron generates a bunch of action potentials in a rapid succession. Boom, 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 boom. It gets me there. So again, oftentimes one action potential is not going to get me there. So I have to rapid fire. The other is spatial, which means a bunch of neurons gang up on a second neuron to get it to threshold. And this right here, this is called convergence, and this is how a lot of your nervous system works, where you have a bunch of receptors that synapse on a second cell to get it to depolarize. All right, the autonomic nervous system is going to be all throughout this course. You should have had this in the MP1. I'm not sure I trust what you learn, but you have to learn the autonomic nervous system inside and out. And there's some key things here. So again, we have the sympathetic, otherwise known as what in simple terms? Somebody? Oh, come on, guys, you must have learned this. Thank you, Cindy. Yeah, fight or flight. All right. That's when you're really super excited or super scared or whatever. And then the parasympathetic that we call, it has several different names. Okay, rest and digest. Very good. Very good. All right, beautiful. So what you need to be able to do me, and here's another test question, is tell me the differences between and the similarities between the sympathetic and the parasympathetic. And this one's slide says it all really. So one of your questions on your test is going to be, what are the similarities? What are the differences of the pathway? So in this question, I don't want to hear fight or flight or rest and digest. I want you to tell me what's going on in this pathway. So what are the similarities? Well, the sympathetic and parasympathetic presynaptic, or preganglionic, I should say, neuron is somewhere in the central nervous system. Before we go any further, can somebody tell me what a ganglion is? Anyone tell me what a ganglion is? See, and this is why I go over this stuff. What's it? A collection of neurons. Okay, Cerise. A group of, not cell bodies, neuron cell bodies. Okay, that's half the definition. What's the other half of the definition? A collection of neuron cell bodies. No. Okay, very good, Suresh. Yes, it's a collection of neuron cell bodies outside the CNS. So it's a clump of cell bodies outside the CNS. So we have what we call the preganglionic neuron. So this is representing a ganglion. It's only showing you one cell. There would be hundreds and hundreds and hundreds of these cells in this ganglion. But we have the preganglionic neuron and then the postganglionic neuron. All right. So let's go with the similarities. So for both the sympathetic and the parasympathetic, the preganglionic neuron cell body is somewhere in the central nervous system, the brain and the spinal cord. That's one similarity. The second similarity is the preganglionic neuron is myelinated. That's for both. The third similarity is the preganglionic neurons for both the sympathetic and parasympathetic release acetylcholine as a neurotransmitter on the postganglionic neuron. The differences are, and this slide doesn't show it all that well, is the preganglionic neuron for sympathetic is really, really short. The axon is short. And the postganglionic neuron axon is really, really, really long. It's the opposite for parasympathetic. The preganglionic neuron is really, really long, and the post is really short. That's one difference. So when I ask for differences, don't say, well, one difference is the preganglionic neuron for sympathetic is short, and the second difference is the postganglionic parasympathetic is really, really short too. That's all the same. So the length of the axon is all one difference. The next big difference is the sympathetic postganglionic neuron releases norepinephrine, whereas the parasympathetic releases acetylcholine. So study that. There's a slide coming up that will summarize all that. So again, these are reflexes, just like you should have learned in the first similarity is all the preganglionic neurons for both sympathetic and parasympathetic are somewhere in the CNS, either the spinal cord or the brain. There's a slide that's going to summarize that for you in just a little bit here. And again, just a quick thing. A lot of this autonomic nervous system is reflex. You don't have to do anything. Autonomic does its own thing regardless of what you're thinking. So they use reflexes that are similar to the patellar tendon reflex. All right, so you have receptors, stretch receptors, whatever. The afferent is one neuron. If you remember way back when, probably not, it's a unipolar neuron. And then we have a 2-neuron pathway to the organ that's going to get it to do something. All right. So in this particular example, you eat some food, you have stretch receptors, and that'll send a signal there that, hey, there's food in there. And then you have a reflex that says, okay, let's digest that thing. And this is just kind of a summary slide that you should study. That goes over all the differences in a different way. So again, I'm not going to, there's one thing I do want to go over because we're going to use that a lot in this course is we have, well, I have a slide that's coming up here, so I'll wait. So remember, we'll talk more about the adrenal sympathetic pathway when we talk about the endocrine system. So don't worry too much about this right now. So again, here we see that the parasympathetic and sympathetic release acetylcholine on the postganglionic neuron, and then the postganglionic neuron for parasympathetic releases acetylcholine, and the sympathetic releases norepinephrine. And we'll talk more about that later. And this is just a fun slide. It kind of gives you a visual of how it's organized. So you see the sympathetic has a short preganglionic neuron that synapses on ganglion that ride right along the spinal cord, and then they reach out and they touch all your organs. Whereas the parasympathetic has a very long preganglion that goes all the way to the organ, and then you have an itty bitty postganglionic neuron that actually targets the organ itself. And so they go, and most of these are going to be antagonistic. And you can see that the spinal nerves make up most of your sympathetic, their cranial nerves, and your sacral nerves make up the parasympathetic. So, any questions? I know it's a lot of information, but it's supposed to be a refresher. All right. Okay, Danielle, you have a question?
Yes, sir. I was just making sure that even though it's a refresher, and apart from the ones that you said are going to be on the test, we should still know some of this information, right?
You should know all this information.
Okay.
Nothing in this, this is called essential concept because everything that I'm presenting to you, you're going to see throughout this course. Everything. I handpicked the stuff out of AMP1 that I know you guys are going to need in this course. All right, so everything in here is important. Some more important than others. Mm-hmm. So for your comedy, for your humor, yep, as Kay said, this is all going to be on your first test. So this is old stuff that will be on your first test. Okay, and then my little humorous thing is, so this came out of an anatomy book, but the artists felt compelled to put underwear on this person, which I was like, really? Anyway, maybe you don't see my sense of humor in that, but yeah. It could be underwear, or maybe it's a bathing suit from the 1950s. I don't know. Anyway. All right, let's move on. We're almost done here, folks. All right, so here's your summary slide. So this is what you're going to study for the differences of sympathetic and parasympathetic. And so the similarities are pretty straightforward. All right, a little bit more here. Okay, so hopefully this isn't too new to you. So a nicotinic receptor is a cholinergic. And think about that, folks. When you see the term cholinergic receptor, you think acetylcholine. So cholinergic receptors bind to acetylcholine. You have a nicotinic receptor, which is just a sodium gated channel. It's always excitatory. So way back when you learned muscle physiology, all those receptors on your skeletal muscles were nicotinic. But you also have muscarinic receptors that again bind to acetylcholine, but they are G protein linked receptors. And they do a lot of different things depending on the organ, the function, and whatnot. So take a good hard look at the ones that we know that exist and tell me, somebody impress me, tell me only two that I'm going to ask you to know, test purposes why. You take a moment to read those. Which ones do you absolutely have to know? Anyone? Okay, Christina's got one, definitely the M2. Oh, come on, Daniel. M1 through M4. I said two. That's okay. Come on, guys. Which two have the most words? Thank you, Cindy. Yeah. Yeah. All right. And again, what you should have targeted, M2, heart. M3, lungs. All right. So I need you to know the M2 and the M3. Okay. Beautiful. And this one's kind of silly. M5, location is not well known. You know, that's from the last textbook I looked at. So anyway, all right. Here is a really, 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 really important slide. I don't know how many reallys that was, but anybody count? Okay, I need you to know this, folks, because you're going to see a lot of this. Okay, I think it was 3. All right, because this is going to explain how your parasympathetic controls so much of your organs. All right, so study it thoroughly. As I said before, the nicotinic is always excitatory. It's the one that's in your neuromuscular junctions, and it's going to be the receptor that's going to be on the postganglionic neuron. So it's always excitable. The muscarinic can do all kinds of things. It can be excitatory or inhibitory. The primary way it's inhibitory is it opens potassium channels. And here I go back. I sound like a broken record now. Remember, if I open a potassium channel, which way is potassium always going to go? Everybody, 1, 2, 3. Out. Yeah. And since it's positive, it's going to make the inside of the cell less what? Or more what? Positives are leaving, so I'm more, very good. I'm farther away from threshold. I'm hyperpolarized. Very good, folks, good. All right, and that's how it works in the heart. If I want to slow my heart rate down, I open potassium channels, I become hyperpolarized, which slows the heart down. Now, this is the courtesy of Katie, because I hated the slide that the artist came up with, because it was very confusing. So Katie, with her magical skills, came up with a better slide. So my point is not all 3 of these events are going to happen on the same cell. These are just 3 ways I can excite a cell, depending on what the cell is. So I could close potassium channels, or open sodium channels, or open calcium channels. And we're going to see these. I open a sodium channel. Like we've said, sodium's always going to rush in, depolarizing my cell. Or I can open calcium channels. calcium is going to rush in. Remember, sodium and calcium are both higher outside the cell. Now, who can impress me and tell me why closing potassium channels would cause the cell to depolarize? Why would closing potassium channels cause me to depolarize? Anyone? It has everything to do with something that's not on the actual membrane that you see. Okay, Sarah's opening. Well, okay, we're closing this. Why, remember, okay. I'm closing the potassium channels. Potassium can't leave. I'm going to give you a hint. But potassium is building up inside the cell. It's building up. It's increasing. It's increasing. What caused it to increase? What are we not seeing on this slide? What are we not seeing on this slide that would cause potassium levels to increase inside the cell? Come on, folks. You can do it. I close potassium channels and potassium. Why, though, seriously? Why are my potassium levels rising if I closed all of them? No. Your hint was it's not really on the slide. What's making this happen? Well, Christina, I don't know what you, just one word answer. Diffusion, what? There's no diffusion happening because I've closed the channel. What is, all right, and I'm just going to give you the answer here. Okay, well, that was Katie, so that was, Remember what's always going on, the sodium-potassium pump. The sodium-potassium pump is always pumping potassium inside the cell. If the potassium can't leave, the potassium levels are going to rise, and it's positive, and that's what gets me the threshold. I know that was a lot, okay? So never forget that throughout this course. The sodium-potassium pumps are always doing what they are intended to do. When do the sodium-potassium pump, when does it quit working? Who can tell me that? When does the sodium-potassium pump stop doing what it's doing? Anybody? When do my sodium-potassium pumps stop working? No. This is a very simple question. It's kind of a joke question. Well, it does when, Nita? When do they quit? Thank you, Sarish. That's exactly what I wanted to see. Okay, that's better. That's what I want to see after the execution chamber. Nice one, Andy. Yeah. So that's kind of a joke, folks. They never stop until you're dead. Beautiful. Study this, all right? Study this and understand closing potassium channels will get a cell to depolarize, all right? Because I'm pumping potassium in. And this is how it works in a lot of your organ systems. All right, let's move on. We're almost done here, folks. Bear with me. We got a lot of stuff done today. That's great. So adrenergic is for our epi and norepi. All right, and then once again, they can be excitatory or inhibitory. And again, we have different types of adrenergic receptors. Okay, so you have alphas, A1, A2, betas, B1, B2, and B3. And again, they have different functions depending on the organ system. But once again, there are three that are the most important. And I've already given you a hint based on what I just talked about in muscarinic receptors. So somebody tell me, which ones do you need to know for the test? Cindy, alpha and beta are all of them. So, okay, yeah. Hopefully you saw heart and you saw beta 1. Okay. Alpha 1, yes. And 2. Excellent. All right. And of course, that answer was on the next slide or so. Okay, so yeah, it's important that you realize, and we'll cover this in greater level when we get to the vascular system. But yeah, when you have a fight or flight response, we don't want blood in our GI tract or viscera of any kind. We want the blood where? Where do I want my blood, folks? Fight or flight. Where do I want all my blood to go, or most of my blood to go? Real quick answer. Come on. There's a bear. Where do I want my blood to go? Very good, Daniel. Yeah, I want it to go to my skeletal muscles, all right? I don't need to be digesting or doing all that stuff or whatever. So yeah, so the alpha 1 makes sure that the blood doesn't go to the GI tract. We want it to go to the skeletal muscle. And yes, beta 1, because it's got that heart rate thing in there. And beta 2, yes, because it has the lungs and bronchodilation. All right, so that's good. And again, there's just a summary, but the ones that you need to know are right there. All right, very simple. Alpha 1, get the blood out of the skin, the viscera, get it to the skeletal muscles. Alpha 1, yeah, beta 1, get my heart rate going. And beta 2, get my lungs opened up. I need oxygen and I need blood to fight the bear. All right. And again, just most of your organs have dual innervation, and it's kind of like a back and forth, depending on your state. And this is just kind of, there's nothing really highly testable on this other than realize that a lot of your autonomic is on the reflex. There's no conscious, input here really, unless you're scared. And that's what this means when you see the limbic system, the cerebral cortex. Think about this. If everything's cool, you're just chilling out, your parasympathetic is in control. But if you have something that, again, excites you or scares you, then you're going to go into sympathetic mode. And it's different for everybody, I personally like snakes. So if I see a snake, I'm going to go, hey, that's cool. What a nice snake. I'm not going in the sympathetic mode. But if you are scared of snakes or whatever, then you see a snake and you're going to go full on into your fight or flight, your sympathetic response, and override that. So each of us is different depending on what excites us or what scares us. Okay. Snakes are cool. Anyway. And like I said, a lot of things are at the reflex level, like especially like urination, defecation, erection, all that stuff. You don't need your brain. If they're in a tank. Yeah. They're behind glass, I guess. Okay. So that's not a big thing there. I just want you to understand that under normal circumstances, the hypothalamus is in control. You're not consciously knowing what's going on there, but you can override that if something excites or scares you. And here's the last horrible slide. Oh my God. What does that mean? What does that mean?
It's on the test.
It's on the test. It's green, which means what? It's importante, but what is the V word I'm missing?
You need to know it word for word.
There you go. Very good. Very good. Exactly. This is really important because this is the whole crux of this entire course. So the hypothalamus is the boss, all right? But don't put that on the test, all right? That's all right. So it's going to get information from everything, all right? Some of it's going to be indirect because it'll go through the thalamus, which you should have remembered was your relay station for all sensory information. It controls the sympathetic and parasympathetic, as you're going to learn on Wednesday, all right? And you're going to also learn that it controls the pituitary gland, It is the big, what's so amazing about the hypothalamus is we consider it part of the endocrine system, but it's also part of the nervous system. So it's like right there. So the joke in the class is if I ask you a question on a test and you don't know the answer, just put hypothalamus. You might just get it right. You never know. All right. And some of the other things, it induces emotions and behavioral drives. What we mean by that is it is the hypothalamus that tells you when you're hungry, right? It's the hypothalamus that says you need to get some sleep, or you're thirsty, or it's your hypothalamus that says I'm feeling kind of frisky right now. All right, so it does all that emotional behavioral stuff. It coordinates your voluntary stuff with what you don't have control of, the autonomic. And yeah, the other ones, it regulates your body temperature and it coordinates your circadian rhythms. All right. This is just a joke, folks, this bottom thing here. This is just something I remember decades ago when I took A&P. But I thought it was kind of funny. So the 4 F's: feeding, fighting, fleeing, and whatever your favorite F word is for that. But do not put that on the test. That's just for you to go, ha-ha. Okay. All right. So beautiful. All right, folks, we knocked this out. Good session. And we're on our way. Yes, Derek.
Yes.
Derek, you have a question?
Yes, I'm here. Thank you so much. I'm so sad that I missed the phase of class. How's the nature of the exams? Is it going to be online for that I know? Is it going to be on a lockdown browser?
And where are you going to learn all that stuff, Derek?
Online.
From?
Group me.
Okay.
Yeah.
And your syllabus.
But it's, so because I don't want to waste everybody's time. It's getting late. But again, all your tests are online. They're all essays. They're all critical thinking. There's no proctor. There's no lockdown. So you're going in there and like I said, nothing's stopping you from trying to go to your references or sources, but the tests are timed. So if you're spending all your time looking up stuff, you will not finish. So these are timed, and once the time runs out, you're done. And that's what it is. But hopefully your classmates will give you a little bit more detail of what that's all about. So these will be online. And you put it any way you want, but if you don't study, there's no way you can complete the tests on time before it shuts down, and then bad things happen. Any other questions, folks?
Thank you so much.
But work together, guys. Remember, it's you guys against me. All right, so work together. Any other questions? All right. Yes, Jennifer.
If we do have a question while we're studying throughout the lecture from today, can I just send you a text about anything if I feel like I have questions about, or
Of course you can.
learn a bit more about this certain topic?
Of course you can.
Okay, thank you.
I hope I made that quite clear to everybody. You're more than welcome to text me anytime about anything. Okay? So don't hesitate if you have a question about anything. All right?
Thank you, Professor.
Okay. Yeah. That'll work for tonight. We'll talk more about that. We have a couple days before the first test, so we'll cover that. Okay. Oh, have a good night, folks. And I will see you on Wednesday. And thanks for participating from most of you. That's what makes this so much better when people participate. Have a good night.